Genesis Love, and I wanted to talk to you today about how sometimes the limits of our understanding seem to create these paradoxes that we cannot resolve. Our understanding of the universe has long been built on foundational rules that seem to define the nature of reality. From Newtonian mechanics to classical physics, these rules were thought to be universally applicable and unyielding. However, as science has progressed, particularly in the realms of quantum mechanics and cosmology, many of these core principles have been challenged. This has led to the emergence of paradoxes that often defy our conventional understanding and remain unresolved in contemporary science. This video will explore 10 key paradoxes from the wave particle duality to the Fermi paradox, which challenge fundamental aspects of reality and remain subjects of intense debate and investigation in modern science. One of the earliest and most significant paradoxes to emerge in the 20th century was the wave particle duality of light and matter. The paradox was discovered in the early 1900s, most notably through the work of Albert Einstein and Louis de Broglie. Einstein's explanation of the photoelectric effect showed that light behaves as discrete particles, which he termed photons. Meanwhile, de Broglie proposed that matter, such as electrons, could also exhibit wave-like properties. This dual behavior, where particles can act as both particles and waves, depending on the context, defied the classical rule that objects must either be particles or waves. The wave-particle duality continues to pose a profound challenge for understanding the nature of reality, as it suggests that the properties of objects can be both discrete and continuous at the same time. The concept of time and its direction has also been called into question by both quantum mechanics and the theory of relativity. According to classical physics, time flows in one fixed direction, from the past through the present to the future. However, the advent of Albert Einstein's theory of relativity in the early 20th century introduced the idea that time is relative and can be affected by gravity and speed, with time slowing down near massive objects or when traveling at high speeds. This was discovered around 1915. Quantum mechanics has introduced scenarios where particles can exist in superposition, simultaneously occupying multiple states at the same time. These discoveries challenge the notion that a constant unidirectional flow and suggest that a more complex and malleable nature of temporal reality exists. Another paradox that arose with the development of quantum theory's Heisenberg uncertainty principle was formulated by Werner Heisenberg in 1927. The uncertainty principle states that it is impossible to simultaneously know both the exact position and momentum of a particle with absolute precision. This uncertainty challenges the classical idea of a deterministic universe, where all properties of an object should be knowable. Instead, the uncertainty principle suggests that there are fundamental limits to how we can know about the state of a system. This has profound implications for the concept of reality, as it implies that particles do not have well-defined properties until actually measured, creating a paradox where knowledge itself is limited by the nature of observation. Quantum entanglement is another mind-bending paradox that challenges the classical notion of separateness and locality. Discovered by Einstein, Podolsky, and Rosen in the 1930s, this suggests that quantum particles can become entangled, meaning that states are linked regardless of the distance separating them. When one particle's state is measured, the other particle's state is instantaneously determined, even if two particles are light years apart. This phenomenon seems to defy the principle of locality, which states that objects can only be influenced by their immediate surroundings. Quantum entanglement appears to imply that information can travel faster than the speed of light, a concept that directly challenges the foundation of relativity and Einstein's theory of causality. The grandfather paradox, which is often discussed in the context of time travel, presents a scenario where the very act of traveling back in time can create contradictions in the timeline. The paradox suggests that if someone were to go back in time and prevent their grandfather from meeting their grandmother, it would result in the time traveler never being born, thus preventing their ability to travel back in time in the first place. This paradox raises questions about the consistency of time itself, as it challenges the idea that events are fixed and immutable. Though the grandfather paradox is often a thought experiment rather than empirical discovery, it highlights a key issue in the conceptualization of time and causality that remains unresolved in both theoretical physics and philosophy. Stephen Hawking, 1992. In the realm of black holes, one of the most perplexing paradoxes is the black hole information paradox, which challenges our understanding of information conservation. In the 1970s, Stephen Hawking discovered that black holes radiate energy through what became known as Hawking radiation. According to these calculations, the radiation that causes black holes to gradually lose mass and eventually evaporate, the key problem being that this evaporation process seems to erase any information about the matter that once went into the black hole, violating the fundamental principle of quantum mechanics, which holds that information cannot be destroyed. This paradox remains unresolved as physicists struggle to reconcile the law of quantum mechanics with the nature of black holes. We also have the many worlds interpretation of quantum mechanics, which presents another paradox that challenges the idea of a singular reality. Proposed by Hugh Everett in 1957, the many worlds interpretation suggests that every time a quantum measurement occurs, all possible outcomes of that measurement actually occur, each in a separate branching universe. This creates an infinite number of parallel universes, each representing possible different outcomes. The paradox here is that this interpretation fundamentally changes the classical view of a single deterministic reality and instead suggests that the universe is infinitely branching into multiple realities, which we cannot directly perceive or interact with. While this theory has gained significant attention, it remains one of the most controversial interpretations in all of quantum mechanics. In cosmology, the discovery of dark matter and dark energy has posed a major paradox, as these entities exert gravitational forces and influence the universe's expansion, yet they cannot be directly observed. In the 1930s, astronomer Fritz Zwicky observed that galaxies within clusters were moving faster than expected, leading him to hypothesize the existence of unseen dark matter that accounted for the extra mass needed to explain their motion. Later, the discovery of the accelerating expansion of the universe, attributed to dark energy, further complicated our understanding of the cosmos. Despite their profound influence, dark matter and dark energy remain invisible to current detection methods, challenging our understanding of the composition of the universe. The observer effect in quantum mechanics is another paradox that has troubled scientists for decades. It suggests that the very act of observation or measurement influences the state of a quantum system, leading to different outcomes depending on whether the system is observed. This paradox was most famously illustrated by the double slit experiment, in which particles like electrons behaved as waves when not observed, but they behaved as particles when they were measured. This raises a fundamental question about the nature of reality. Does the universe exist in a definite state independent of observation, or does observation itself play a role in shaping the outcome? The observer effect challenges the classical view of an objective reality that exists independent of our perception. Finally, the Fermi Paradox presents an intriguing challenge to our assumptions about the existence of extraterrestrial life. In the 1950s, physicists Enrico Fermi and Michael Hart noted that given the vast number of potential habitable planets in the universe, we should have already encountered evidence of alien civilizations. However, despite the sheer number of stars and planets in the galaxy, no definitive signs of extraterrestrial life have been found. This paradox raises questions about the rarity of intelligent life, the potential for civilizations to self destruct, or the possibility that extraterrestrial life exists in forms or locations that we are unable to detect. In conclusion, the paradoxes discussed in this video highlight the limitations and contradictions in our understanding of reality as revealed by advancements in quantum mechanics, cosmology, and other areas of physics. While each paradox challenges core assumptions about the universe, whether its nature of time, consistency of information, or the very structure of reality itself, these unresolved issues continue to fuel scientific inquiry. As our tools and theories evolve, it is likely that some of these paradoxes will be resolved, while others may lead to even deeper questions, underscoring the complexity of the universe and our place within it. If you like this message, please like, share, and subscribe. If you're new here, welcome aboard. This is a safe space. If you're returning, I'm glad that you're back. I thank you so much. Your support makes this channel great. In the name of the Most High God, I wish you health, wealth, prosperity, and abundance, blessings and protection if you so deserve it. Woodman signing off. Have a wonderful and blessed day. Take care.